Hello to everyone. In this lecture, I am going to discuss about the block diagram reduction methods in control system. So, before going into the detail of the block diagram reduction, I would like to discuss what is block diagram reduction and what is the transfer function. As you have already studied that what is the transfer function, what are the components of the transfer function, how will you plot, what are the poles, what are the zeros, and how will you draw the pole zero diagram for a given transfer function, and how can you comment on the stability of the transfer function. So, first of all, what is the block diagram reduction? It is the simplification of block diagram via certain arrangements. And what is the transfer function? Transfer function is the ratio of Laplace transform of output to the Laplace transform of input, considering all initial conditions 0, or considering the system is initially relaxed. Suppose the transfer function, suppose Hs is a transfer function, and you can define Hs is equal to Ys by Xs, where Y where Ys is output and Xs is input, or you can say Ys is the response and Xs is the excitation. You can write like this S plus A1, S plus A2, S plus A3 upon S plus B1, S plus B2, S plus B3. So, this is the transfer function, and from here we can define the poles and zeros from this given transfer function. So, we can find the poles by making this denominator 0, and we can find the zeros by making this numerator 0. So, as we know that S is nothing but sigma plus j omega, this is the complex frequency, real plus imaginary part. So, we can define poles are those complex frequency. We are getting poles by making the denominator 0. So, if I am making the denominator 0, so we can get, or by making this denominator 0, we are making this Hs infinite. So, poles are those complex frequencies which makes the transfer function infinite, and zeros are those complex frequencies we are making. For getting the zeros, we are making this numerator 0. If I am making this numerator 0, then this whole transfer function will become 0. So, we can say zeros are those complex frequencies which makes the transfer function 0. In this way, we can define the poles and zeros. Poles are those complex frequencies which makes the transfer function infinite, and zeros are those complex frequencies which makes the transfer function 0. Poles and zeros are denoted by, poles are denoted by cross and zeros are denoted by circle. So, this is the procedure how can you define the poles and zeros, and you can denote the poles and zeros. By getting the value of poles and zeros, you can show the pole zero diagram like this. This is the real part, this is the imaginary j omega. You can give the positions of the poles and zeros in this plane. So, this is all about the poles and zeros. This is the crux of the poles and zeros and transfer function. Now, coming to the rules for reduction of the block diagram. So, first of all, and basic method is blocks, if the blocks are connected in series or cascade. Series or cascade means the output of the first system is connected to the second system. So, it means it is connected in series, the output of first system is working as a input for the second system. So, you can see, if I find the output of the system 1, input for this system is US, the output for this is US into G1S. This output of the system 1 will work as a input for this system 2. So, what will be the output? US G1S into G2S. As you know that if I am talking about the any system, xs is the input and ys is the output. So what will be the value of ys? Ys is nothing but the input multiplied by the forward gain or gain of the system. So ys will be equal to xs into gs. Following this method, we can write the output of system 1 and system 2. So in we can combine the output. If these two systems are connected in series, then the multiplication of their individual system, multiplication of gain of their individual system will give the output or combined gain of the cascaded blocks. I mean to say, you will get G1s into G2s as a gain of the cascaded system and US will be the input. It means US is same as input, US is same as input for this cascaded output, but the gain of the systems has been multiplied. So individual gain of the systems are multiplied when the blocks are connected in series. Next is blocks are connected in parallel. So how will you identify whether the block is connected in parallel or they are connected as a feedback? So you have to identify if the forward path is connected with the summing point in right direction. I mean to say, if the forward path is connected, then you can say that these paths are in parallel. I mean to say, suppose US is input for both the systems. So this is G2, this is not G1. So US, the output for this, output of the block G1s is US into G1s, output for block this G2s is US into G2s. So here I am using the summing point. This will add output of both the systems. So you will get here US G1s plus US G2s. So what will be the combined output? Combined output will be like this, and you can say if two individual systems are connected in parallel, then their gain will be added, and if system is connected in series, then their gains are multiplied. So you can say here, if the systems are connected in series or cascaded, then their gain will be high as compared to the systems connected in parallel. Third is feedback loop. So you can see here, this is the standard canonical form of the closed loop system, in which negative feedback is given here and positive feedback is given here. So we can find here, this is the error signal ES and this is the feedback path, output of feedback path. Suppose this is BS. So you can derive the output for both positive and negative feedback system. But you have to, for this you have to find the output of each path. So you can write here ES is nothing but US minus BS, because we have taken here negative feedback system. So what will be the output here? US minus BS. What will be the value of BS? BS is nothing but YS into HS. This is nothing but BS. Now we have to find the transfer function YS by XS. So what will be the value of YS by US? What will be the value of YS by US? ES is equal to this, BS is equal to this. You can put here BS is equal to this. So what will be the, and ES is, you can write here YS is nothing but ES into GS. Now you can put here US is equal to, ES is equal to US minus BS and BS is equal to YS into HS. So I am writing here YS is equal to ES is nothing but US minus BS into GS, and BS is nothing but YS into HS. So I am writing here YS into HS. US minus YS into HS into GS. So I am transferring this negative with negative sign. So you will get here YS 1 plus GSHS is equal to US. So we have to find here YS by US. So what will be the value of YS by US? YS by US is nothing but YS by US is nothing but GS upon 1 plus GSHS. So this is the transfer function of the standard closed loop canonical form with negative feedback system. So this is the, if I am using the positive feedback, then in that case this positive sign will become negative. The procedure will be same for finding the value of YS by US. So in this way we can find the transfer function of the closed loop canonical form. Next is we can interchange the summing point. The condition for interchanging the summing point is that there should be no block in between the summing point. Whenever we are performing such type of operations, we have to remember that the output should not change from this. If the output is changing, then it will be difficult to implement these methods or rules for reduction of block diagram. So we have to remember this whenever we are implementing or whenever we are performing reducing the block diagram, then we have to see that the output should never change. So the input for this summing point is U1 and U2. Output of this summing point is U1 plus minus U2, and the third input is U3. So the combined output for after getting this U1, U2 and U3 as an input, we are getting this U1 plus U2 plus minus U2 plus minus U3. So if I am changing this summing point, interchanging this summing point, then the output should be U1 plus minus U2 plus minus U3. So if I am changing this, I am putting this U3 here and U2 here. So you can see here the output is U1 plus minus U3, and again you are getting the same output U1 plus minus U2 plus minus U3. So the only condition is that there should be no blocks in between these summing points. Then we can interchange the summing point. Moving a summing point after a block. Moving a summing point after the block. So what is the summing point and what is the takeoff point? If I am talking about the standard canonical form, so this is the takeoff point and this is the summing point. So we are going to perform the operation by moving the summing point after the block and before the block, by moving the takeoff point before the block and after the block. So next is the moving a summing point after the block. So this is the I have already told you that the condition is that the output cannot change after performing any operation. So before moving the take or summing point after the block, the output is U1 plus minus U2 multiplied by GS. So if I am moving this summing point after the block, then what will happen? If I am moving this summing point after the block, then this is the I am moving this summing point after the block US. I am moving this summing point here. If I am moving the summing point here, then what will be the output? This is US, output for this block is U1 GS and U1 GS plus minus U2. This will be the output, but the desired output is GS into U1 plus minus U2. Then what will I do? I will do the necessary changes for getting this output in the summing point. So what changes is required? We require the output GS into U1 plus GS into U2 plus minus GS into U2. So what will I do? I will add a block with gain of GS. So by adding this block, we get this output that was previous output. So you can see here GS U1 is the output here, and after passing this input to the block GS, we are getting the same output which I was getting in the previous before modification. So whenever we are moving the summing point after the block, then we have to add the gain of that block in the second input. I mean to say, I am moving this summing point to the after the block, then we will multiply this input with the gain of the block, जिसके बाद हम ट्रांसफर करना चाह रहे हैं उस ब्लॉक से, उस ब्लॉक के गेन से we will multiply, then we will get the same output. Next is moving a summing point ahead of a block. Now we want to move this summing point before the block. So before the block, if I want to move this, then what is the output here? GS U1 plus minus U2. If I am moving this, then we will get the output moving the block without any modification in the input U2, then we will get GS U1 plus minus U2, which is not a desired output of the previous system. So now what will I do? If I am moving the summing point before the block, then we will divide the gain and multiply by the input 2. So I will divide the gain of that block before which we want to move the summing point. So what will be the output here? We will get the output here U2 divided by GS plus U1. When we will multiply this, we will get the same output GS U1 plus minus U2. So these are the methodologies for reduction of the block diagram. Next is moving a takeoff point after a block. Moving a takeoff point after the block. We want to move this block after move this takeoff point after the block. So if I see here, the output from this takeoff point is U. So this is UGS. The output of takeoff point is U, and the final output is U into GS. If I move this takeoff point here, then the output of takeoff point will become U into GS, but this is not desired. Desired is U. So what we have to do? We have to multiply it by the inverse of the gain of the block, or you can say you have to divide by the gain of the block of the system after which you want to move the takeoff point. So you can see here the final output is UGS, and the output of the takeoff point is U, which is of previous system. So this is the method. If you want to move the takeoff point after the block, then you have to multiply it with the inverse of the gain of the block after which you want to move the takeoff point. Moving a takeoff point before a block. Moving a takeoff point before the block. After the block you are getting here, the output is UGS. The output of takeoff point is UGS. So if you move this takeoff point before the block, then the output will be, output of takeoff point will become u, but the desired output of takeoff point is UGS. Then what you have to do, you have to multiply with the gain of the system GS with the input u, then you will get the output of takeoff point as UGS. So this is the method. How can you implement, how can you reduce the blocks given to you? Moving a takeoff point ahead of summing point. Moving a takeoff point ahead of summing point. Now you can see here, this is the summing point. So u1 and u2 will pass through the summing point and you will get the output like this, u1 plus minus u2. And what will be the output? Output is again u1 plus minus u2 of the takeoff point. If you are moving this takeoff point before the summing point, then what will happen? Here you are getting u1 plus minus u2. If you are moving this takeoff point before the summing point, then what will you get? You will get here only u1, but the desired output u1 plus minus u2, then you have to add this u2 using the summing point. So if I am moving this summing point here, without this summing point, the output is u1. u1 is this. Now the output for from the previous system is u1 plus minus u2. So for maintaining this output u1 plus minus u2, we have to add this u2 with this u1. Then you will get the output u1 plus minus u2, and the desired output will be like this. So here if you are getting here u1 and you have given here u2 with the summing point, the output is same, but the output of takeoff point is different without adding this summing point. So for if you want to move this takeoff point before the summing point, then you have to add the second input using the summing point, then your output will be same. Now moving a takeoff point beyond a summing point. Takeoff point को summing point से आगे ले जाना है. Again you can see here the output of takeoff point is u1. If I am moving here, then the output of this takeoff point will be y. So for getting this u1, what will I do? I will again use the summing point, but the polarity of the input u2 will be different. u1 plus minus u2. If I am moving here, the output will be u1 plus minus u2, but the desired output is, takeoff point का output मुझे क्या चाहिए? u1 चाहिए. Then I will use here minus plus u2 for maintaining this equal to u1. So what will I do? I will add the summing point here with the reverse polarity, with the opposite polarity, minus plus, so you will get here u1. So these are the methods how can you reduce the block diagram, and you can follow any method. The basic method for this is, you can use any rules that I have told you up till now. You can use any rule, but you have the standard method is that first you have to reduce the cascade connection, after that you have to reduce the parallel connection and after that you have to try to make the given block diagram in standard canonical form. You have to try to maintain, you have to try to make a standard canonical form, or convert the given block diagram into a standard canonical form. So these are the rules for reduction of block diagram. You have to follow these rules for simplifying the block diagram which is having many blocks, summing points and takeoff points. So first rule is check for the blocks connected in series and simplify. So first you have to identify whether how many blocks are connected in series or cascaded, and you have to simplify. After that, second rule 2 is check the blocks connected in parallel and simplify. So you have to check the blocks whether these are connected in parallel and you have to simplify. And rule 3 is that check for the blocks connected in feedback loop and simplify. Feedback loop and simplify means you have to check whether is there any connection which is in standard canonical form of the closed loop control system, then you have to simplify that block. If there is difficulty with takeoff points while simplifying, shift it towards right, and if there is difficulty with summing point while shifting, shift it towards left. So third and fourth and fifth rule is that you have to shift the summing point towards left and takeoff point towards right. So the basic methodology for shifting the takeoff point left and takeoff point right is that if you are doing this if you are trying to bring this in practice, then you are trying to convert the given block diagram into a standard canonical form. So if you see the standard canonical form, you can see that the summing point is on the left side and takeoff point is on the right side. So if you are bringing the takeoff point towards right and bringing the summing point towards left, then it will be very easy to simplify the given blocks and you will easily get the simplified expression of the block diagram. So these are the rules. Now I am coming to the example by I am coming to the example in which you can see that how can you reduce the block diagram. Let us take an example this. So we have to find the value of CS by RS. So this is the very simple block diagram in which you can see here that this is the standard canonical form and this is also the parallel connection. So first we have to identify, whenever we are solving, whenever we are reducing the block, when we are performing the block diagram reduction, then we have to identify how many blocks are connected in series, how many blocks are connected in parallel, and is there any connection which is giving the standard canonical form of the closed loop control system. So it is clear that this is the standard canonical form of the closed loop system. This is also clear that these are connected in parallel and this is the feedback path. So we can see here step 1 will be this is the canonical form. So first of all we will reduce this block. So after reduction this block, I will get G1 upon 1 plus G1 H1. So we can follow, we can reduce this. First we can reduce this parallel connection, but you can, it is clear from the block diagram. So you can directly do this conversion, or you can directly reduce. So I am writing here, this is step 1, this is step 2. So after step 1, I am getting the output G1, sorry, G2 plus G3 plus G4. So I can reduce this, I can again draw this block like this, RS G1 upon 1 plus G1 H1, this is H2, G3, G2 plus G3 plus G4, again G2 plus G3 plus G4. This is CS, this is RS. Now you can see here, this is, these two blocks are connected in series. So we can write here G1, G2 plus G3 plus G4 upon 1 plus G1 H1. So now you can see here, this is the standard canonical form of the closed loop system. So we have converted this into a standard canonical form. Summing point is on the left side, takeoff point is on the right side. So you can again convert this and you can get the value of CS by RS by simplifying this. So these are the methods how can you simplify the block diagram of the by using the techniques that I have told you. So first I have simplified this parallel connection. After that I have simplified this standard canonical form. After doing this, we get these two blocks are connected in series, and after that I have modified this and we get G1, G2 plus G3 plus G4 upon 1 plus G1 H1. And after reducing these two connections, cascade connections, we came to conclusion that the given standard form is in the reduced block diagram is in the standard canonical form of the control system. So we can again get the value of CS by RS by simplifying this. So this is all about the block diagram reduction technique, and we will continue with this block diagram reduction, or I will consider the new topic that is related to the signal flow graph. Thank you.